Welcome back to a new lecture. Today I will discuss about object-oriented design. Specifically, I will emphasize more on the basics of object-oriented design. This is one of the lectures that I will be offering in the lecture series of the course Software Engineering. The topics I will be covering today are gluing the modules from the analysis stage. Specifically, I'll discuss about assigning responsibilities for actions of use case plans to modules. And then I'll discuss about design principles, specifically about the expert doer principle, high cohesion principle, low coupling principle in relation to subsystem decomposition. And at the end of this lecture, I will be elaborating the business policies and the design principles in relation to the business policies. And finally, I'll show you how to model the problem domain by using class diagram, and I will adjourn this lecture. So in the previous lecture, when we talk about use cases, I tried to discuss a bit about system sequence diagrams, where in this type of diagram, we show interaction between external users to the system. Okay, so the system is depicted as a middleware between various users, which serves as an input, or which serves as an enabler for the overall system that you are building. So here we do have, for instance, a user at one end and a timer at the other end. So we can consider these two as uh, actors for this system. But as you can see from this diagram, the system is a black box one. We do not know what's inside this system. So if the dynamic modeling technique is hiding the internal implementation details of your system to be, but only shows interaction between users, specifically external actors, in this system, or collaborating with this system, then that kind of dynamic modeling is called system sequence diagram. So as I already discussed, system sequence diagrams represent interactions between the actors. So here we can also consider the system as an actor. But mainly from this diagram, one thing we can generalize is that the system is represented as a black box, and all other external entities or actors are there in a way the sequence diagram shows. But when we elaborate more on, or when we dive more on the system sequence diagram, here we do have external actors. These actors could be human beings or any other components or softwares or APIs, okay, that has a relation with the system. But when we further dive into the internal implementation of the system, or the composition of the system, the general system, or at the design phase, the system to be, we can identify various objects, the objects that has relationship between them. It could be by data flow or control flow. So every system will have at least a controller. Okay, every system will have a controller. In most cases, a system will have a storage or a persistence model, and also some types of controllers are there, but we can also say boundary objects are also constituting components of a given system. So when we see inside the system in a system sequence diagram, then we see objects and interaction between these objects. So a sequence diagram, or a dynamic modeling technique that shows interaction between modules or objects that we have identified inside the system, is called module sequence diagram. So to distinguish between module sequence diagram and system sequence diagrams, system sequence diagram, as we have already covered, represents interactions of external actors, including the system itself. But module sequence diagrams represent interactions of modules inside the system. So here in the system, which is the black box one, in the case of system sequence diagram, in the case of module sequence diagram, this will be further expanded into various objects that interacts with each other. We'll see more about this module sequence diagrams in the next consecutive slides. So there is this metaphor for software design, a metaphor for software design. By that we mean a very good exemplary term that describes what we are supposed to do while building or designing a software. It's called connecting the dots. Okay, so assuming we have a system as a box and everything inside that system is modular, since we have already said software engineering is all about implementing a divide and conquer approach, that divide phase of the software engineering process creates modules. And software engineering is all about, or software design is all about connecting those modules or connecting those dots. So whenever we design or when we intend to design a software system, we first start with the system sequence diagram, which is a generic version of the system to be or the software to be. So the system sequence diagram shows only actors in the system as a black box, as we already said, and its purpose is to design the internal behavior using concept modules from the domain model. So here we have two distinct things. The first one is system sequence diagram that shows a relationship between or interaction between actors, assuming the system is some kind of black box. When we say something is black box, it only accepts inputs and generates outputs. We do not have any information out in the implementation detail of this kind of components or systems. So the second step, by starting from the system sequence diagram, the second step would be to design the internal behavior of this black box system. And the technique we use to design the internal behavior of this black box system is called module sequence diagramming technique. And module sequence diagram mainly bases on the domain model or the problem domain model that we have specified in the requirement engineering phase. There are three major responsibilities of objects, since we are talking about object-oriented design, and specifically since we are talking about dynamic model design using system sequence diagram and module sequence diagram. It's very important to discuss about the responsibilities an object could have. The first responsibility an object could have or undertake is knowing responsibility, which is about memorizing data values, collections, or references to the other objects, and it could be represented as attributes. The second responsibility of an object inside a dynamic model is doing responsibility. The first one, it's knowing, it's more to storing, memorizing. The second responsibility of objects is doing. When we say doing, it's about performing computations, data processing, control of physical devices, and it's represented as methods. Okay, so objects that are supposed to know something are represented as attributes or states in object orientation, but objects that are supposed to do something or perform some computation or data processing or control something like physical devices is represented as methods. So these are the two building blocks of objects in object-oriented design paradigm. The first one, state, the second one, behavior. State stands for attributes or can be correlated to attributes, and behavior is directly proportional related to methods. So these are the two major responsibilities of objects in object-oriented software design. The third responsibility is delegation responsibility. By that we mean delegating subtasks to objects dependencies, and it's represented as sending messages, or in some cases we can also refer to it as method invocation. Let's take some example regarding delegation responsibilities. What you see here are delegation responsibilities identified for the system function enter key. We have been discussing about this scenario for smart door system, and in that smart door system or lock system, there is this function called enter key. The user, if he or she intends to enter into its house or her house or his house, he has to or she has to enter the key to the door lock or the locker function or system. So the delegation responsibilities of an object responsible for this system function enter key could have the following responsibility descriptions. The first one, for instance, send a message to key checker to validate the key entered by the user. This is, again, it's about sending or method invocation, so it's a delegation responsibility. Send a message to a device controller to disarm the lock device. This is also one use case or one scenario in the system function enter key, which is again delegation responsibility of an object assigned to perform this device control. Again, send message to device control to switch the light bulb on. Again, this is also another responsibility of an object assigned to this task or system function. We can go on like this for all the other delegation responsibilities. So this is how you simply identify the responsibilities of objects. Or even when you plan to, identify objects, you can identify by this taxonomy, by using these three taxonomies: objects that should know something, objects that just should perform something, and objects that should invoke methods or send messages to other components, objects that should communicate with other components. So you can classify or create a taxonomy of objects and reorganize them in these three compartments. That makes the system design, especially dynamic model design, easier than the traditional or classic ones. That being said about responsibilities of objects in object-oriented software design or system design, now I will be discussing about assigning responsibilities. When we say assigning responsibilities to objects, we are then talking about designing diagrams, okay, or design diagramming techniques. So basically, when you start designing your software by using some dynamic modeling techniques such as system sequence diagram or module sequence diagram, you are recommended to use hand-drawn sketches so that you will not be deceived by the colorfulness of computer-generated designs. So the first recommendation for any software engineer or system designer is that to sketch the design, the dynamic model of the system to be using easy to find items like pen and white paper. So you don't have to make it fancy, but you have to give much emphasis for the control flow and data flow, or for the validity of control flow and data flow, rather than for the attractiveness or for the appearance of the design or the diagram that you are building. So there are two types of designs or diagramming outputs that you could find while working in assigning or while assigning responsibilities during object-oriented design. The first one is hand-drawn creation or design, and the second one is computer-based unified modeling language specification of the design. So the one you see to the left of this screen is created is supposedly created by hand manually. The one to the right side is computer-based UML specification of some other design. So here we are describing, a sample or a template or an exemplary designs, high-level designs for module sequence diagram, both in case of hand-drawn design and also computer-based UML-based designs. So there are two purposes of design diagrams. The first purpose is as a communication tool. You could use it to communicate with your programmers, customers, end users. So this is a very good tool to communicate with the stakeholders of the system during the creative process, during the requirement engineering process even. So for that purpose, it's recommended to use hand drawings and take an image by phone or camera to communicate with the user or any other person. This is mainly due to the fact that you don't have to waste time on polishing something until you feel confident that you reached a good design. So the first thing to do while design diagramming is that you have to give 100% of your time on validating the process, the control flow, data flow of the dynamic design, rather than polishing it to make it look better in the eyes of your customers. It should look correct and accurate in the eyes of your customer rather than beautiful in the first phase. Okay. The second purpose of design diagram or design diagramming is specification as a specification tool for documentation. So in this case, when you start discussing about the possible ways of specifying your hand-drawn diagrams, it's recommended to use unified modeling language type standard specification tools. So just for the case of specification, you have to use UML design tools, and produce presentable and professional looking diagrams. But at the early stage of design diagramming, its purpose is mainly for communication. So in that case, you shouldn't waste much time in polishing it, but you can simply hand draw it and communicate it with the user by taking the camera or the image by using simple cameras or your phone camera. Okay, that is the general principle or recommendation given by customers and software engineers in the area. So we've been talking about the metaphor of system design as connecting the dots. So here we start by mapping what we have been discussing in the domain model, the problem domain model, to modules or compartments or components in the design phase, and see how we can connect the dots. So here we start with the use case. When we start connecting the dots or designing the diagram or design or model the dynamic aspect of your system, we start with the use case, which is the last output we got from the requirement engineering phase. So assume we do have a use case one for unlock. Okay, this is simply a task or plan of action to unlock the door in the case of a smart door system. So the scenarios in this use case were: first, user enters the key code, then system verifies that the key is valid, then system signals the key validity. This is basically the success scenario. And then system control triggers in two cases. The first one, lock device to disarm the lock, and light switch to turn the light on. So this is what we got from the requirement engineering, right? This one from the requirement engineering. So you are going to decompose or identify objects from this use case by following all steps that this use case might implement or undertake. So here, the domain model from this use case, we call it the concept module, because still now we are not talking about system design in general. We are just talking about modeling the problem domain. So we just model the problem domain, which is the use case, by using concept modules. So that these components, these boxes that you see to the right side of the screen, can be considered as concept modules or domain representatives of domain model. This is mainly due to the fact that we generate these boxes or the contents inside these boxes from the use cases that we got during the stage of requirement engineering. So if you see here, there is a boundary object called key code entry, which is identified from here because it says user enters the key code, right? So from there, we can generate key code entry boundary object. Another boundary object is status display. We can discover the need for a boundary object called status display from this diagram. For instance, the system verifies that the key is valid, and the system should signal the key validity to the user, right? So this needs some boundary object called status display or something to display the response of the system back to the user. So for that purpose, we just added one more. And in this system, we do also have a user, right, that enters the key code and accepts the verification of entered key codes. So for this purpose, we identified one user from here in the concept modeling part and two boundary objects. We can further go to another one. For instance, here we identified an entity called key checker. The reason we came up with this concept called key checker is that it says the system verifies that the key is valid. So the object, the responsible object to verify the validity of this key should be something with a name related to key checker. Okay, you can also say key validator or key verifier or something like that one. Okay, and throughout this sequence of actions scenario, we have been saying system, right? So for all these interactions between modules we have identified so far, we need to have a central controller which is representative of the operating system where your system to be will presumably rely on. So for that purpose, we identified a control object called controller. The same is true for all other components or modules, which we call them concept modules, and we call this process domain modeling, identifying modules from use cases. Okay, this is how you identify modules from use cases. The very first step in connecting the dots or in designing system in object-oriented way. Then the next step would be gluing the modules by plan walkthrough. That means we have already identified objects here in the concept module identification phase or domain modeling phase. The next step would be gluing the modules. Okay, gluing the modules is directly related to the metaphor we said connecting the dots. So how can we glue the module? Here we have a domain model from use case one or a concept module from use case one. So we have here list of actions that a use case one might go through. So here we have again a scenario walkthrough that helps us to glue the modules which are already identified in the domain modeling phase. Okay, in order to glue the modules identified as a concept module, we have to come up with a walkthrough scenario. The purpose of this walkthrough scenario is for mapping a use case plan of action to the domain model. Okay, so we can ask questions like the following to come up with connectivities between these modules. The first one, who handles this data? Okay, who handles this data? It comes from the first scenario in the use case, or the first action in the use case. It says user enters the key code, so user will be identified here. So in addition to that, in the domain modeling or concept modeling phase or concept module generation phase, we say or we identified some boundary objects, right? Interfacing objects like key code entry and status display in relation to the first two actions of use case one. So for that purpose, this question, who handles this data, can be answered with interface objects and controller. So controller is responsible to mediate between every interaction in your dynamic model. So for that purpose, we identify controller and interface objects, or as we said, boundary objects are engaged in this process. So this is the first question that helps you to identify the relationship between domain model and the use case. Okay. The other question, who performs the verification? Depending on this one. So these are questions that you should come up with by yourself, depending on the nature of the use case or the problem domain. Okay. So who performed the verification? Based on what data? So the key checker verifies. We already identified the key checker here as a verifier, right? We also give it a name called key validator or key verifier. Again, based on the entered key code, the data will be entered key code. So here for that, we have persistent model. We said it's entity, and the entity will have key, right? We also identified the responsible component key checker as an entity in the previous phase. Then, for instance, the other data would be stored valid keys, because validation can only be made against already stored valid keys. So once you identify the connection between concept modules by asking various questions that helps you to identify who is responsible for what task, okay, and who does what, which is again directly related to the compartment of responsibilities that we have seen so far, which is knowing responsibility, doing responsibility, and delegation responsibility. Your questions should be sorted in a way they directly align with each of these responsibility categories. Okay, so once you connect the dots or glue the modules by after asking such kind of questions and generating their answer for those questions from the use case, then the second step would be to design a dynamic diagram or a module sequence diagram. Okay, so in order to design a module sequence diagram, you have to first sort the concept modules you have identified before in their order of usage according to the use case, and then try to track or plot the sequence of actions that could be undertaken by the use case. So the sequence of actions could be atomic, or it could be sequential, or at some point in time it might have conditional paths. So for all this, sequence diagram has mechanisms to represent or to model such dynamicities. So this, for instance, shows how a system flows from object called code entry to controller. This is a very simple hand sketch diagram. When we come to the second diagram, for instance, we do have code entry object, controller object, and checker object. It shows a high-level interaction between these three objects through the controller. Okay, for instance, the communication between a checker and a controller object is by a function or method called check key, because the purpose of the checker, as we already declared before in the previous slide, is to verify or to check the key. Even its full name is key checker. So you will have some type of method or some type of function for every interaction between controller and entities, or boundary object and controllers, or objects and objects in general. So due, like, as a consequence of this kind of operation, we call it scenario walkthrough, you came up with information about the interaction between modules, and by using the concept modules you have identified before during domain modeling, and the answer you got for all sorts of questions you asked in the phase of scenario walkthrough, you build the sequence diagram, the module sequence diagram. So this module sequence diagram is responsible to represent or model the dynamic aspects of your system to be in general. So we have been discussing about mapping, use cases to concept modules, and then actions to modules specifically. So we have already done this mapping in the previous slide. Just to summarize what we have been doing there, the possible list of questions that you can ask for use case one, which is for unlock use case, and for the sequence of actions presented here, could be the following questions, like who handles this data, who performs the verification, and based on what data, who signals based on what data, who signals based on what data. This kind of questions are related to each of these actions presented as a sequence of actions in the use case one. So you can ask a lot of questions. That these are sample questions for you, but you can raise many questions in the phase of scenario walkthrough to come up with very well articulated, well identified, well analyzed interaction information or metadata for modules identified during domain modeling, or for concept modules identified during problem domain modeling phase. So as you already said, once you identify the concept modules or the modules in general, and by using the scenario walkthrough, once you identify communication between these modules, possible interaction between these modules, the resulting diagram or model will be sequence diagram or module sequence diagram. So here, for instance, we do have an example for the unlock use case, which is use case one. We do have code entry object, controller object, checker object. Some more objects are there. We'll talk about these objects later. Again, we do also have another object called lock device control, and interaction between this is also shown here. Okay, in this sequence diagram, as we already said, these are modules. Here, this shows the vertical bar shows lifespan of the object, okay, or the activity of the object. For instance, this object is active from here to here, okay. Whenever the object is not needed in this sequence diagram or dynamic model, you have to show it's not required by using X sign at the end of the lifespan. But if you have the tendency to use this object somewhere in this sequence diagram, then you might have to keep it active for some time. So here, this shows a control flow. The horizontal arrows show the control flow and data flow. The top ones are objects, and the vertical bar is basically to show the lifespan of the object. Specifically, the activity of the object is represented by this rectangular vertical boxes. So this object, for instance, might be active up to here, and from here to somewhere here, it might be inactive, and based on some request around here, it might be active again, okay? For instance, if there are some requests coming from the controller, you might have to activate this object again. So this box, a very thin rectangular box, vertical box, shows where the object is being invoked or used. and where it's not, and the other one shows without the rectangular box shows the object is in idle mode at that time. So this is basically a time series, okay? The lifespan bar. So the horizontal one is a control flow bar or arrow or a data flow arrow that shows the flow of data from the initial point to the final point, okay? So the questions have helped us to come up with, such kind of interactions between objects that are important to model the dynamic aspects of your problem domain. So when we design, for instance, if you assign two or more software engineers or system designers to design the dynamic model of the same use case, then they might come up with different sketches for the same problem, for the same solution. Okay, so these are, for instance, alternative designs for the first use case. In the first one, you see controller, checker, and log device control. The flow of data and control is from the controller. Then there is this function that asks the checker to check for the validity of the key. Then the checker component or object checks or compares the entered key with the one stored in the database. And then it will, if assuming the success story, success scenario, then this checker activates a lock device controller to unlock the door. This is one scenario. So in this case, for instance, the controller triggers check key function, and the checker again compares and activates the device control directly. But when you come to the second alternative, for instance, to the right side of this screen, we do have the same number of objects here, but the control flow is a bit different. So here, for instance, the controller triggers the check key, which is the same as the previous sequence diagram. But again, the checker compares the key for validity. Once it checks the validity of the key, it doesn't directly trigger the lock device control, but it returns the control back to the controller. And finally, the controller will be responsible to trigger the lock device control so that the door will be unlocked. So in principle, both of these designs, dynamic models, works if a programmer takes this one and implement or design a software, develop a software, the software works. And again, if another developer takes this design and implement software, again, this software works. But as a software engineer, we have to choose between different alternatives of dynamic model. And mainly, we have to give much emphasis to um, responsibilities. So, for instance, the responsibility of a controller should not be shared by other objects. So here, for instance, in the first case, the controller should be responsible to flow controls from one point to another point. Okay, it should use or it should assign some delegations to other objects, or other objects should be only undertaking delegation responsibilities, but this controller should be able to coordinate between different objects. That is the essence of dynamic modeling. So in the first case, this has been violated because the checker is directly triggering the device control. So in this case, the controller, which is the central brain for your dynamic model, do not have any or does not have any information about what's happening here because it hasn't been consulted. But in the case of the second one, the checker has consulted or acknowledged the validity of the key, so the controller will know the person who entered this key is the correct one, the eligible one, and it can directly trigger the device control that opens unlocks the door. So the second one is the best approach. We'll talk about this kind of selections in the near future within the next slides. But which design is better? We already said the second one. And how to evaluate the goodness of a design? This is mainly by considering the responsibility of objects. So when you create one object, it has a dedicated, or it will have a dedicated responsibility. So its responsibility should not be shared with other objects. So this causes irresponsibility or lack of accountability between objects, and also it might cause inconsistency between the flow of control and the flow of data in a given dynamic model. So how data travels? Because here in dynamic modeling, we have been talking about the flow of control and data. So let's see how data travels. The first option in the previous one, you see, in the previous sequence diagram is that in the first option, key checker passes the information, the validity of the key, to another object controller, which uses it to perform some work and then activate the lock. So that some work is activating the lock. So this is basically the second option. Okay, the data flows from the controller to checker, and from checker to controller, and the controller to the device control. So this shows the same data flow. In case of alternative B or option B, the key checker directly uses the information, which is key validity, to perform some work. That work is activating the device control. So this is directly related to the wrong approach. Okay, the wrong approach. So the advantage of the wrong approach might be shorter communication chain, because here it doesn't have to communicate back to the controller, so it might have shorter communication chain. But the setback or drawback of this kind of approach is extra responsibility for the checker component. So here the checker component is responsible to first compare K to KS and then activate the device control. So this is excess responsibility for checker. The controller should be the one with excess responsibilities if need be. Okay, so for that purpose, it's not recommended to use such kind of data flows in your dynamic model. So what are the characteristics of good designs? The first one, it might be contradictory when we talk about the characteristics of good designs, but you have to balance between these trade-offs. The first characteristics of good design is shorter communication chains between objects. So in case of this, the second approach could be better than the first approach, because the second approach is this one. It has shorter communication channel. But the second characteristics of good design is balanced workload across the objects. Okay, this is mainly due to the principle of divide and conquer. Okay, so you have to divide as much as possible equal load of tasks to each modules or objects identified in your dynamic model. Okay, so the first one, this short communication, and the second one might contradict with each other in some scenarios. For instance, the scenario that we have seen before. So in this scenario, we have shorter communication for the second one and longer communication for the first one, but we are choosing the first one. And in some cases, the first one has a very good balance between tasks among these objects are well balanced, because the controller has its own task, checker has only validation task, controller again has another task. So, and again, lock device control also has different tasks. So the second criteria to say something is good, or something that is good, is that if it has balanced workload across the objects. So the main principle of software engineering, which is divide and conquer, should divide the system into manageable modules or objects. The other one is low degree of connectivity, specifically association among objects. So one object should not be connected to all other objects unnecessarily. So this will cause simple, or this will make the system prone to failures. Okay, so for that purpose, if some design has objects which have high degree of connectivity, then we can classify that design as a bad design. But if modules or objects in a given sequence diagram, for instance, has reasonably fair amount of connection with other objects, then we can classify this as good design. For instance, a system with this kind of hub modules is more prone to failures, because if this one fails, all the other modules are dependent on this hub module, then they will consequently fail. So this type of design is not recommended. So that being said about the good and bad design techniques, let's see some design principles. Here we see three major design principles. The first one is expert doer principle. In this expert doer principle, the concept is that modules that knows should communicate information to those that need it. So you shouldn't engage extra modules or unwanted modules in a given control flow or dynamic model. but only the Oracle modules, only the expert modules, or only modules that are responsible to take some action should be assigned that task or that action. Okay. So for instance, we can consider one scenario: how to recognize a violation if a method call passes many arguments. This is one scenario, for instance, for us to give much emphasis for expert dual principles, in which modules do what they are supposed to do only. The second one is high cohesion principle. So there is this two kind of contradictory principles in software design. The first one is cohesiveness, and the second one is coupling. So when designing your system, when identifying your modules and interaction between these modules, first you have to try to increase cohesiveness among uh, classes or components is inside a single module. Okay, each module will have different classes or submodules inside it. Then those submodules should be highly related to each other. That's one principle. The second principle is regarding relation between different modules, intra-module communication or interaction. If you have to identify modules separately, then those modules should have low coupling, or a relationship among those two modules separated should have low degree of relation. Okay, so this can also be discussed from the point that modules should not delegate responsibilities in many tiny parts. This will increase ultimately the relationship between dissected or fine-grained modules, and it's against the principle of low coupling, coupling of software design. That being said about the three major principles of software design, it's also, on the other hand, very important to give much emphasis to the need to compromise some of the principles of this system design. So any non-trivial design, is a compromise between desire and the possible thing to do. So you may have to trade off between some requirements, okay, while designing your system. So to this end, design principles may contradict each other. For instance, balancing low coupling and high cohesion can be a trade-off in software design. Sometimes you might have to increase cohesiveness between classes inside a given module, but at the same time you might want to balance the problem or the principle of low coupling, or you might want to preserve low degree of coupling between modules. So this is in most cases contradictory, so you have to find a balancing spot for these two depending on the nature of your software or system to be. The other one, low coupling, for instance, offers flexibility, right? If you have a very low degree of relationship, or if one of your module has low degree of relationship or interaction with other modules, then failure in other modules won't affect it. So in a way, it increases the flexibility of your system. But this low coupling or fine graining different tasks into different places might introduce complexity. Okay. On the other hand, high cohesion simplifies maintenance, because in one module you are going to have very similar type of classes, but again it may lead to overlay granular modules. So the goal is to find the right balance based on project needs. So that being said about the need to balance between these contradictory design principles, it's also critical for others to know how the designer resolved each compromise or trade-off, so some new guy coming to that project can evaluate the reasoning. So for that, documentation is very important in addition to the code itself. Okay, so as a software engineer, you should really give much emphasis to documentation, commenting, and building, wiki files and version control systems in general. So we have asked which design or which alternative of dynamic model is better. So from what we have discussed so far, it's recommended to use the second alternative, which really gives much emphasis to the delegation of the right responsibilities to the right objects. Okay, but in some scenarios, this might be the perfect one. Okay, for instance, if you really want to give much emphasis for low degree of connectivity between objects, or short communication paths, then you might choose the first option. But by comparing the pros and cons of these two approaches, you might choose the best one for your environment, or for the problem at hand. Designs or system designs should be responsibility driven. We have already discussed about this one, because I said you have to compartmentalize your objects based on the three compartments of responsibilities. Okay, knowing responsibility, doing responsibility, and delegating responsibility, or delegation responsibility. So from this end, what we can say is that the first step should be identifying the responsibilities, and the second step, for each responsibility, identifying candidate modules or objects to assign to should be done. Then at the third step, we have to consider merits and trade-offs of each alternatives by applying the design principles we have discussed so far. And finally, we have to document the reasoning process for your selection, and that would help the sustainability of the system development and also the system itself. So this is near to complete use sequence diagram for the use case unlock. So if you can see here at the top, we do have objects. We have the controller object, key object, checker, key storage, device control, photo observation, and logger. So here, for instance, photo observer, then this object could be something that processes the camera feed from your home. Logger could be some component that writes to your database or file that logs some information. Device control, as we already discussed, is an object responsible to open or lock or unlock the door. The key storage is where you check the validity of the key. It's kind of database. Checker is another method or class that checks the validity of the key, which for instance, if you consider this checker object, you can consider it as a class. In the last lecture, you told me that Java, so you can consider this checker as a Java class in which there is a check key instance method. Okay, so this will check the possible outcomes for the entered keys. We do also have an object for the key. The key is something that is fed by or input by the user. So to see, for instance, one success scenario for the first use case unlock, the user enters a key. So for this, we need method. So by the way, implementation can be directly mapped from this sequence diagram. So here, for the user to enter key, we need to have some function, enter key, for instance. Then the lifespan of the controller starts here, as you can see. Then the controller creates key. Then the key again asks for the validation of key by invoking a method check key. Then this check key invocation or check key functionality invocation is directly to the checker object. Then the checker object does this one. It will iteratively check for all stored keys, and in each iteration it compares the given key with the stored key. And at any point in this iteration, if it gets the validity of, or if it asserts the validity of the key given, then it will return back to the controller some kind of acknowledgement, as you can see here. Then after getting the acknowledgement, the controller logs this transaction by the key and validation pair. Then this is directly logged to the object called logger. So the lifespan of the logger starts here. Look, it has been idle from here to here. Now it starts to do something, which is logging the pair of key and validation information, which is most likely Boolean information. Then after that, look here, the controller is the main brain, as we already said before. So you should use the controller as a main brain for your control flow and data flow. Okay. Then after that, we do have some alternatives here. We have seen about different alternatives, right? So alternatives are also specified like this. In the first alternative, for instance, if validation is true, that means if the key is correct, then the controller will activate lock. Okay, so it will be activated. The activate lock function is here in the device control. Then it will be activated. This is in the first scenario. Then also the controller triggers is daylight function, which is a function of photo observer. So we perceived photo observer as an object that takes inputs from the camera, but it's I guess a different kind of sensor, which is a light sensor rather than a camera. Okay, then we just took the first option, but the optional one in this alternative would be the daylight is equal to false. For instance, here we have a checker that checks whether the daylight is on or not. If there is no daylight, then the light of your house should be on for that purpose. The second option here, opt, is DL is equal to false, then activate bulb will be triggered. The device that's responsible to activate bulb, or the object responsible to activate the bulb, is the device control, as you can see here. And the lifespan of this device control was at idle stage here, okay? And again, since it is re-invoked, it will be active and likewise works smoothly throughout the overall control flow and data flow in the dynamic model. So whenever a system or an object finishes its task, it should be marked, or the days of that object should be marked with this X sign. Okay, it should be destroyed. This is very important because during implementation, for instance, you have to cancel or you have to clean objects which are no more usable from your memory, right? So for that purpose, the designer should show when the programmer should kill the object from the memory. So this is a very important diagram, the sequence diagram. So we can go on and on like this and finish the total, the possible combinatorics of actions in this unlock use case. But since we have already covered major part of this use case, it's easy for you to track to the terminating point of this dynamic model. So the second variation for the unlock use case would be this one. You can check this one by yourself, okay? Some conditions are specified here. The way it does is different from what we have seen here, okay? So it's better to see what part of, or what aspect of control flow, what aspect of data flow is different in this dynamic model or module sequence diagram. This one is also another variation, okay, another variation. For instance, here, if you remember, we considered two variations, the first alt here and the second alt here, right? So this diagram shows those variations, how the system reacts to such variations in your system. This is also true for the second variation. That one is for the first variation. So just to summarize the design variations that we have noticed in the case of unlock use case and the corresponding sequence diagram for unlock. Here we have the main use case, so the main sequence diagram or dynamic model. And here we have one alternative, one variation here. The second variation is here, okay, extended here, and the third variation here. So the same use case could be, the same use case could be dynamically modeled, considering in our case three different alternatives. Okay, three different alternatives. So for instance, the first alternative is when validation is true. Okay, the second alternative is when validation is false, and the same is true for others. Okay, you can check what happens when some Boolean expression is turned to true or false. So this ABC shows those different variations. So now, are we done with the use case one unlock after discussing this much about it? I mean, after refining the design to this extent, are we done with the unlock use case and its corresponding sequence diagram? Not exactly, actually. This is mainly due to the fact that such kind of dynamic modeling requires time, and you have to check it iteratively and eliminate any outliers or any false assumptions in your sequence diagram. Any unconsidered things should be considered, any false assumptions should be corrected. So in a way, you have to update or enhance your sequence diagram so that the programmer will use it flawlessly, okay, during the implementation phase. So the problem with the use case one, for instance, which is the unlock use case and the corresponding dynamic modeling is, first, we didn't check that the user is at the right door. The sequence diagram doesn't consider that. The second one, it didn't distinguish critical and non-critical functions. For instance, what if log transaction call to logger does not return? So what does your system do? This kind of detailed design consideration should be taken. For instance, in some cases, you might have to label some functionalities as optional or you know not important. So if you get the response from them, it would be nice. But if not, you might have to proceed with your operation as a function, right? So the previous sequence diagram does not have such kind of specifications. So for that, we are not yet done with use case one and its corresponding sequence diagram. The other one, for instance, adding new household devices causes major design changes. We haven't considered that here. Controller has several unrelated reasons for future changes, for instance, regarding business policies and device management. So these all things should be considered while designing the dynamic aspect of system to be. That being said about the the need to consider, and dive more into the analytical aspects of your dynamic modeling. The other component or the other concept that I would like to discuss with you today, actually, we have discussed this concept in the early chapters of the software engineering course. This concept is business, this topic is business policies. So what do we mean by policy? Let's explain this one by example, for instance. Let's declare one policy. For the smart home case or for the smart door case, we have this sample policy. It says if key is an element of set of valid keys, then disarm lock and turn lights on. Else, another mechanism. Increment failed attempts counter. If failed attempts counter equals maximum number of unload, then block further attempts and raise alarm. So this is directly inherited from the business policies that we generated or identified during the requirement engineering process. So every logic that you define during the system design or object-oriented design in general comes from the business policies which are formulated during the requirement engineering process. So this is a very important consideration, for instance. So your sequence diagram should consider this kind of policies for it to work as per the requirements of the end user. The last topic that I will be discussing here is the class diagram. The class diagram is more to sequence diagram, but it's mainly specific to the relation between those objects, and it's more to detailing the objects identified during concept module identification or problem modeling. So class diagram should be again derived by looking up the sequence diagram. Okay, so for instance, here we do have sequence diagram, and in this sequence diagram we have various objects. So the input or the source for class diagrams is this objects from sequence diagram. So if there are some objects which are idle in this sequence diagram, then you might eliminate them and you might not consider them as a class. Okay, so this is almost one step before implementation, class diagramming. So for that purpose, you have to validate, you have to refine the objects in your sequence diagram and come up with a very neat list of classes and interaction between them. So class diagram basically corresponds to the static module structure for conceptual analysis, but it's very detailed and refined in comparison with the sequence diagram. You might have various classes with different types of relationships. Here, for instance, this has an inheritance relationship. Here we have a base class. Here we have a leaf class or a child class. The above one is a parent class. Here we have kind of association or aggregation relationship between a container and a child class. The same is true for all these classes. For instance, from the unlock use case and from its corresponding sequence diagram, we were able to identify classes like photo observe, key storage, you see, key checker, controller, logger, and device control. But the detailness of these objects identified in the process of class diagramming is higher than the detail of objects in sequence diagram. So for instance, here in in the realm of object orientation, the object or a class is a combination of state and behavior, right? So if you see, for instance, the controller here, it has state, which are attributes, and behavior, which are methods. These methods also has different access modifiers. We call this access modifiers. These are ways to implement information hiding in your system. So this hash is to say this attribute or state is protected. This plus is to say this method is public, and this minus says the deny more attempts method is private to this controller class. The same is true for all other ones. So here from the class diagram, what we can get is that first the name of the class, the name of the class is here. For instance, for this one, key is the name of the class, and the state of the class, at least the specification, code, timestamp, door location for key class is there. This one might not have methods, but in case of, for instance, controller, it has methods like enter key and deny more attempts. So from class diagram, we get states of the class in addition to name, and again, behavior or methods of the class. That's one. The second one, relationship among classes is also depicted here. Okay. For instance, here key and key storage has one-to-many kind of relationship. Here again, controller and key checker has a relationship again. Controller with device control has a one-to-one relationship. Controller with logger has kind of one-to-one relationship. So class diagram shows what state and what behavior objects are there, with what class or with what other object are they connected, what type of relationship do they have. All this is clearly and in detail represented or modeled during the phase of class diagram. Okay, during the phase of class diagram. So we have been discussing about traceability of your designs in the previous chapter, which is about use cases. The same concept comes here when we talk about traceability of your system design. So you have to be able to map between your classes, identified classes, and domain concepts or concept modules. Okay, so in the previous phase, if you remember, in the previous phase, we have identified concept modules, you remember? So you shouldn't just disregard or reject these concept modules once you start diagramming classes. There is one need for correlating or mapping your classes with the concept modules, and that is done by a technique called the traceable matrix or traceability matrix. So in the traceability matrix, in the column wise, you will have software classes, and in the row wise, you will have concept modules. Okay, so you should be able to map each concept modules to any other class or software classes. So if you fail to map any concept module to a specific software class, then you should document the reason behind it. So sometimes the concept modules might be irrelevant when you get to know more about the system. So you have to write the reason behind not mapping your concept modules to software classes by using this traceability matrix methodology. That's all for this chapter. We have discussed about the basic principles for software design. We specifically discussed about how we can map from problem domain models to the dynamic models, specifically system sequence diagram and module sequence diagram. And further, we have discussed about the different principles of designing your system to be. And finally, we discussed about the mapping between objects in the sequence diagram to the class diagram, which is the more detailed form of objects and their relationship. Thank you.